These Gatos here. In this video, we are going to cover the binomial theorem. I want to begin by expanding these four binomials, and we're going to use the patterns that we discover after expanding these to know how to expand something to the fourth or fifth or sixth exponent. So if we start with what the definition of a binomial is it's two terms separated by add or subtract. So let's just look at the very simple x plus y binomial. So when I raise it to the zero, any base raised to the exponent of zero just equals to 1. If I have x plus y to the 1, any base to an exponent of 1 just equals itself. So I end up with x plus y. X plus y squared. Well, when I square something, it means to multiply it by itself. So x plus y times x plus y. So I expand it, and then I group my middle terms, my like terms in the middle there, to get x squared plus 2xy plus y squared. In the last one, I'm going to look at x plus y cubed, which just means x plus y multiplied by itself 3 times. Well, we already know what x plus y times x plus y is, so I can take that and multiply it by another x plus y. So again, applying the distributive property, I get that polynomial, and then I group my middle terms, the x squared y's with the xy squareds. Group those, and I get this polynomial here. So now that we've expanded 4 binomials, I want to look at the patterns that we can find in these. First of all, I want to talk about how do I write binomials when I expand them that have 2 different variables. So the first thing is that the variables have to be written in alphabetical order, x and then y. And then whichever one comes first alphabetically, in this case x, write it in descending order. That means getting smaller. So notice my exponent goes 3, 2, 1, and none. So that's just a convention that we want to use when we're writing these expansions. Okay, let's look at the first term. So the first term is called x, and I want to look at the patterns of the exponent when I expand. So first thing that I notice is that we start with whatever the exponent is. So 0 starts with 0. 1, exponent of 1. 2 and 3 start with that exponent. So every single one of those start with whatever n is on the outside. And then look at what happens when we have more than one term. I start with 1 and I go down to 0. I start with 2 and I go down 1 and then 0. I start with 3 and I go down by 1, 2, 1, 0. So for the first term, the exponent will always start with an exponent of n. N is the exponent on the outside, and decreases by 1 until you reach 0. Well, let's look at a pattern in the second term. So second term of a binomial, we'll call it y. So in this one here, let's look at what happens to the exponent. So if I look at all of the first exponents for y, I notice that they all start with a 0. So that's my first pattern. They all start with 0. And then look what happens. It goes 0 up to 1. 1 is the n value. This goes 0, 1, 2, stops at the n value. This one, 0, 1, 2, 3, stops at the n value. So it looks like my pattern is I start with an exponent of 0, and I increase by 1 until I reach n. Well, there's a couple more patterns with exponents that I want to look at. First thing I want to look at is what happens when I add my exponents. So you can see all the highlighted, I add my exponents. So 0 and 0 adds to 0. 1 and 0, or 0 and 1, adds to 1. 2 and 0, 1 and 1, 0 and 2 adds to 2. So it looks like, even in this last one, that the sum of the exponents of the first and the second term will always add to n. That's useful because when you're expanding, you can now have a little check for each one of the terms to make sure you have them in the right order. Another pattern I want to look at is what happens when I take n, the number on the outside, and add 1. So if I add 1, I get these new numbers, but what do those numbers represent? So in this first one, what does a 1 represent? In this second one, what do I have 2 of? In this one here, what do I have 3 of? Well, I see in the first one I have 1 term. In the second one I have 2 terms. Here I have 3 terms. And here I have 4 terms. So if I take n on the outside and I add 1, I just get the number of terms. So every time you expand a binomial, it will always have 1 more term than the exponent. Let's look at the pattern of the numbers. So the numbers in front, these also have patterns. So the first thing I know is that each expansion here, every single one of them, starts with a 1. When I have 2 or more terms, the last term you can see is also a 1. So I start with a 1, but I also end with a 1. Now to figure out the numbers in between, let's look. So this 2, where does it come from? If you look at the step above, the 1 plus the 1, that adds to 2. Let's see if that works down here. For the 3, look diagonally above it, and I can see that 1 and 2 combine to 3. Same thing here. 2 and 1 combine to 3. So it looks like the numbers in between the ones are found by diagonally adding the numbers above it. So what I want to look at is, how do I come up with this number pattern without listing out all the expansions? If I were to take these numbers here, they would form the top part of Pascal's triangle. Now Pascal's triangle has that same rule. For every row, you start and end with 1, and you diagonally add the numbers above. So let's practice writing row 7. So row 7 is going to start and end with a 1. And then all the terms in between the ones are found by diagonally adding above. So here, 1 and 6 add to 7. 6 and 15 combine to 21. 15 and 20 are 35. 20 and 15 are 35. Notice the symmetry that's going on here. 15 and 6 is 21. 6 and 1 is 7. So that's a nice pattern, but if I want to expand something, let's say to the exponent of 20, don't worry, I'll never ask you to do that, I wouldn't want to list out 20 rows of Pascal's triangle. So I'm going to show you a way to write Pascal's triangle using combinations. So again, all about patterns. So look at all these combinations. I just replaced all the numbers that we did on Pascal's triangle with a combination notation. So first pattern that I notice is whatever number n I'm raising as an exponent is what I start with the combination. So for example, when I'm expanding it to the power of 4, all of these are 4c combinations. When I expand it to 6, these will all be 6c combinations. If I want that 7th row, it'll all be 7c combinations. Well, to figure out the numbers that go with it, watch what happens. I start at 0, I increase to 1. 1 is n. I start at 0, I increase to 4. 4 is your exponent of n. So for the 7th row, I would start at 0 and go all the way up until I reach 7. So that would be how you use Pascal's triangle with the row number. Whatever row number or exponent on the outside is what you start your combinations with. So let's put all of this together in this example here. Let's expand x plus y to the exponent of 5. So step 1, look at the coefficients. So I'm raising it to the exponent of 5, so all my combinations will be 5c's. Okay, so remember the shortcut I showed you on the calculator, how to do all of these combinations in one little step? All I have to do on my calculator is enter in 5 with my set brackets for 0 up to 5. And now I can see what all my coefficients are. 1, 5, 10, 10, 5, 1. Now I'm going to take my first term, which is x, and I'm going to raise it to the n, decreasing by 1 till I get to 0. My second term is y, and I write it as 0 increasing to n. So now all I have to do is write this together. So I like to expand vertically, but I write my answer horizontally. So I have 1 times x exponent 5 times y to the 0, which is 1. 5 times x exponent 4y plus 10x cubed y squared plus 10x squared y cubed plus 5, whoops, let's try that again, plus 5xy exponent 4 plus y exponent 5. So expand vertically, write your answer horizontally. Now looking at this, when I have x plus y to the end and I expand it, all my terms will be positive. But when I have x minus y and I expand it, my terms are going to alternate between negative and positive, depending on the exponent. Remember, when you have a negative number raised to an even exponent, it will always be positive. Now, not everything that we expand in our binomials is x and y. X and y just really represent my first and second terms. So let's try an example like this. So 2 minus 3x. So my first term is going to be 2. That's my x value. My second term is negative 3x. Notice it's a negative because I subtract. Pay attention to the signs. Now I'm raising it to the exponent of 4. So all my combinations are going to be 4c's. Then I'm going to take my first term, which is 2, and raise it to the exponent of n, 4, all the way down to 0. My second term is negative 3x, and I'm going to start at 0 and increase until I get n. Now notice what I did there. I use brackets to substitute. Really important, especially when you're dealing with a negative. Now all I have to do is figure out what all these values are. So let's start with our combinations. Remember the shortcut 4C01234? I enter that into my calculator and get my numeric values. So I know it's 1, 4, 6, 4, and 1. So I'm done with my combinations. Now let's move on to my first term. So 2 exponent 4 is 16, 2 cubed, 2 squared, 2 to the 1, and 2 to the none. I'm done with my second. My third term, negative 3x. So anything to the 0 is 1. Anything to the 1 is itself. And now I'm getting into the squaring. So remember, negative base, even exponent will be a positive number. So here this is going to be positive 9. Down here it will be positive 81. But it will be 9x squared. Here, negative base, odd exponent, it will be a negative value. And x is cubed, and lastly x raised to the exponent of 4. So to finish all this off, all I have to do now is just multiply all my number values together and then combine it with x. So multiplying my numbers together just to help me out, and then combine it with my x. So I've got 16 is my first term, minus 96x, plus 216x squared minus 216x cubed plus 81x exponent 4. So that's how it expands, but remember what I told you. You want to write it in descending powers of x. So you start with the highest exponent, which is 4, and go all the way down to the lowest exponent, which is 0. You can always check your answer, and I do recommend it, especially when you only have one variable. So here was my original question. Here is my expansion. And remember, check always happens in the table. So I go into my table and I see y1 equals y2. So that tells me I expanded it correctly. For my last example, I just want to review with you the laws of exponents. We saw these in 10C, so I just wanted to have these in your notes so you could refer to them. So let's try an example where we're going to need these laws of exponents. So I have a squared minus 1 over a. So my first term is a squared, and my second term, notice I wrote it with a negative exponent. That's because we're going to do product law, and it makes it a little easier if the base is the same. So I wanted them to both be a base of a, and then I took the reciprocal to make it a negative 1. Pay attention to the sign, it's a negative, so my coefficient is a negative 1. So I'm raising it to the exponent of 3, which means that my numbers, my combinations, will start at 3c0 and work up to 3c3. My first term is a squared, and I'm going to write that to the exponent of n, which is 3, all the way down to 0. My second, negative a to the negative 1, starts at 0 and increases until it gets to my n value. So let's multiply these together. So 3c1 is 1 times a squared cubed, 2 times 3 is 6. Anything to the 0 is 1. So my first term is a exponent 6. Then 3c1 times a squared squared times anything to the 1 is itself. So I have minus 3a to the 4 plus negative 1 is 3. 3c2 is 3 times a squared to the 1 is itself. Negative base, even exponent, it's positive. And I have a to the negative 1 times 2 for the exponent. So that is just 3 a squared plus a exponent negative 2. You keep the base the same and add the exponents and you get 0. Last one, 3c3 is 1. Anything to the 0 is 1. Negative base, odd exponent, my value is negative. A to the negative 3 times 3 is negative 3. So altogether that would be subtract a to the negative 3. Now, before I write my final answer, I need to remind myself that I always want to keep it positive. So final answers can't have negative exponents. So these are all in descending powers of a, which is great. But what I'm going to do is write it as a exponent 6 minus 3a cubed plus 3. You don't need a to the 0, means there is no a. Minus 1 over a cubed. And now that is positive. So this has all been about expanding binomials. And I once knew a mathematician who was so poor he couldn't afford lunch. He had or could buy no meals. Get it? Buy no meals. So I hope this video helped. If it did, give it a thumbs up and hit subscribe so I can help more mathies like you. And I look forward to seeing you for the next one.